Today we're looking at lesson 6.7, the symmetries of regular polygons. Let's check out our objective today. I can describe the symmetries of a regular polygon in 2 out of 2 problems. So what do we mean by regular? What does this word mean, a regular polygon? A polygon is regular when it gets a lot of fiber. Waka waka waka. No, just kidding. That's not what we mean. What we mean in geometry is that all its sides are the same length and all its angles are the same measure. And we have a couple of fancy words for those properties. Equilateral, if we divide that word into 2 pieces here, equa meaning equal and lateral meaning side, that word basically means that equal sides. The polygon has all equal sides. Similarly, down here, equiangular. Equa meaning equal, angular meaning angle, or the measures of the angles are all equal. So which one of these polygons, based on that definition, which one of these shapes is considered a regular polygon? Well, let's see, this rectangle probably isn't because these sides aren't the same. It's probably not that one. This is a circle, which we said wasn't even a polygon on a previous day, right? Polygons have to have straight sides. So definitely not the circle. This triangle has all different length sides, so not that one either. It must be this last one, D. And this one, let's see, there's 1, 2, 3, 4, 5, 6, 7, 8 sides. And all those sides do look like the same length and probably the same angle. This is what a regular polygon looks like, a regular octagon in this case. And here are some examples of regular polygons. You've probably seen some of these before. The triangle we often call an equilateral triangle. The quadrilateral has a special name. We call it a square. And then all of these we call regular pentagon, regular hexagon, and so on. Heptagons are a little bit unusual. We don't see those very often. 7 sides. But this is a regular heptagon, all at the same length, all the same angles. And then when we get above 10, we generally stop giving them names just because we don't want to remember all those names. Some of them have names, but in general, we'll just call them n-gons, where n is the number of sides. So this, for instance, we're looking at here is a regular 18-gon. There are 18 sides, and they're all the same length. So today we are looking at the symmetries of regular polygons. And remember, symmetries in geometry, we said, maps a shape back onto itself. So first we'll look at the reflectional symmetry. We're going to look at rotational symmetry a little bit later today. So start out with, here are 3 regular polygons. There's a regular triangle, regular quadrilateral, and a regular pentagon. How many lines of symmetry do these regular polygons have? Go ahead and pause the video. See if you can draw some lines of symmetries on these. Or if you printed out the sheet with the shapes, you can cut those out and try folding them. See how many lines of symmetry you can come up with. So on this triangle, you may have noticed it has a line of symmetry there. That one usually pops out to us, so you can fold the left side over onto the right side and they will match. Did you find any others? Maybe if you rotate your head to the side and sort of look at the triangle at a different angle, you can think of this one being at the top. In which case, that line, if I can draw a straight line, that line that goes from that corner to that side would also be a line of reflection. Fold this half over onto this half. And similarly, this vertex up to that side would be a line of reflection. So overall, we have 1, 2, 3 lines of reflection for that triangle. I can't find any others. Those are all the ones that are either bisectors or connected to a vertex. They actually all are. One side's a vertex, one side's a bisector. And it looks like I've bisected all the sides. So all of those are options, and I've connected all the vertices. So I'm not sure where else I could. Everything else seems like it would be off-center. So how about a square? We've talked about a square a few times, so maybe this one will catch more easily. Well, we probably see we can draw a line of symmetry through the center there. And from the top to the bottom as well, like that. And then we also talked about diagonals of a square. That's a line of symmetry, right? We can fold it into triangles. And this is also a line of symmetry, diagonal. So the vertex to the vertex. So how many did we get there? How many total? See, we have 1, 2, 3, 4. We already counted this one. So we must have 4. 4 lines of symmetry for the square. All right, how about the pentagon? How many lines of symmetry did you find for the pentagon? Well, let's see. We probably found this one straight up and down again. Fold that left side over to the right side and they match up. Did you find any others? Maybe we could take the same approach we took with the triangle, where we turn our head to the side and look at the other vertex and pretend that one's on top. So like if we look at this vertex, pretend that's on top. Well, maybe this line that runs from the bisector of the other side to that vertex would also like fold this half over onto this half. Looks like maybe it does. And we have a similar thing going on here with this vertex over to this bisector. Here as well, and this last vertex. So every single one of these, we took a vertex over to its opposite side. Vertex to opposite side, vertex to opposite side, vertex to opposite side, vertex to opposite side. So basically we have one line per vertex. Well, we have 5 vertices, just like we have 5 sides. So this is 5 lines of symmetry. Interesting. Do we see a pattern forming here? Maybe we see a pattern forming. Let's try with a few more. How about a hexagon, an octagon, and a nonagon? Go ahead and pause the video. See if you can use those methods we used on the previous shapes to come up with the number of lines of symmetry for each of these shapes. So for an even number, we have side opposite side and a vertex opposite a vertex. So if we draw this straight up and down line, that'll be bisectors of opposite sides. But then we should be able to do that on any opposite side, right? So those 2 opposite sides and those 2 opposite sides. So we have 3 lines of symmetry so far. But then we also have these lines that we call diagonals, vertex to vertex. There's 1, there's 2, and there's 3. So overall we had 3 bisectors, 3 lines that bisected opposite sides, and then we also had 3 diagonals for a total of 6 lines of symmetry. Now once again, we could try other lines, but I'm not sure where we'd find a symmetry because all these sides are cut in half already, and all these vertices are connected, so anything else would sort of be off to the side of something. So maybe this pattern is going to hold for all even numbered shapes. Should we see? Here's an octagon. It's an even number, 8 sides. So we can bisect opposite sides, bisect opposite sides. Here as well. That one went way off. There we go. Bisect opposite sides, and there as well. So we have 4 bisectors. And now let's do corner to corner diagonals. Let's see. So here's opposite corners. There's 1. Here are opposite corners. There's 2. Opposite corners here, 3. And opposite corners here, that's 4. So 4 diagonals. Diagonals. 4 bisectors plus 4 diagonals is 8 total lines of symmetry. Maybe our pattern is continuing. Maybe? Maybe. Let's see, this one's an odd number. So this one's going to be patterned like our triangles or like our pentagons. Let's see how that is. We have a vertex, and now instead of it being opposite a side or another vertex, it's opposite a side. We don't have sides opposite sides anymore. We have sides opposite vertices. So every vertex, we could draw a line across. Oops, that one didn't quite make it. That bisected the opposite side. We should be able to do that with this one. Once again, I didn't quite get that in the middle. That's a little better. That one. Maybe here. Here, oops. Here. This vertex to this side. This vertex to this side. And each vertex will get a line because each vertex has a side opposite it. So that's one line for every vertex. And we know we have 9 vertices here, so this is 9. 6 for a hexagon, 8 for an octagon, 9 for a nonagon. So can you see a pattern forming? Do you see a pattern in this table? And if you do, can you tell me how many lines of symmetry will an n-gon have? Just a generic n-gon. We don't know how many sides. It has n sides. It looks like all of these regular polygons have the same number of lines of symmetry as they have sides. 5 sides, 5 lines of symmetry. 8 sides, 8 lines of symmetry. So n sides would have n lines of symmetry. And that is exactly the rule we're going to use on these. A regular polygon with n sides also has n lines of symmetry. But remember, we're only talking about regular polygons here. If I drew an irregular polygon, something that looks like this, we can't guarantee that has symmetry, right? I mean, that one kind of does. Maybe I'll draw something that doesn't. We can't guarantee a shape is going to have a line of symmetry at all, but we can for regular polygons. Regular polygons that have all sides equal and all angles equal are going to have lines of reflection, the same number as they have sides. So now that we've covered reflectional symmetry, let's take a look at rotational symmetry. Rotational symmetry of regular polygons. So we have a regular pentagon and a regular hexagon up on the board. And we're asking, how would you find the center of each shape? Let's talk about why we'd want to find the center first of all. When we rotate something, we talk about having a center of rotation, something that we're rotating it around. And when we're talking about rotating something back onto itself, right, we want it to map onto itself, we would probably want the center to be right in the middle of that shape so that it will not kind of rotate away from itself. So we want to figure out what the center is, so that'll be our center of rotation. So how would you go about finding the center? If you were tasked this, somebody asked you to find the center of these shapes, how would you do it? There are different ways to do it. There isn't a single right way. So just think about, what method would you use to find the center? One way we can do it is by drawing those lines of symmetry that we just drew before, connecting this vertex to the middle of the opposite side, connecting this vertex to the middle of the opposite side, and so on. And you'll notice they all intersect in the same place. Over here, we didn't draw all of them. We didn't draw the bisectors, just the diagonals. But notice we don't need to draw all of them. In fact, we only needed to draw 2. Since they all intersect in the same place, we only need to draw one intersection, so two lines. But there are other ways to find the center as well. Maybe you thought of drawing one of these diagonals or drawing this center line and then taking out a ruler and measuring the center. That would have worked too, because these are regular polygons. That would have found the center. Because any single one of these lines, if you find the middle of it, that's going to be where it intersects. They all intersect at the middle of that line. So now if we take the center we just found and we take out some of these lines, we only leave the ones that are lines to a vertex. So we have the center, we drew a line straight to each vertex. It's basically like cutting a pie into even pieces, right? This is sort of just like what it looks like when we cut a pie, except pies are usually round. So when we do that, we create what are known as central angles. This is considered a central angle right here. And notice I've drawn a circle around these shapes because we're thinking of rotating these, right? And we said that rotating traces a circle. So if we think of rotating this, this one's going to trace this circle around and it's going to meet this other vertex here. This one's going to trace the circle around and meet this vertex here. So overall, if we rotated this, if we kept rotating this shape, instead of making concentric circles like most polygons do, a regular polygon is just going to trace one single circle. And the central angles are the angles that it makes out to that circle. So here's the question. If a full circle is 360 degrees, which we know it is, and we've divided this into perfectly equal pie slices, these ones are perfectly equal as well, how much would they measure? How many degrees would they be? How can you figure that out? Well, we'll just take 360 total degrees, divide it by the number of pie slices. There are 1, 2, 3, 4, 5 pie slices, which you'll notice also happens to be the number of sides. So 360 divided by 5. And we may need to do that in our calculator. I think that's 72. So that angle right there is going to be 72. Similar on this one, we have 1, 2, 3, 4, 5, 6 slices, also 6 sides. 360 divided by 6 is 60. So each one of these angles is 60 degrees. So now, if we think about the rotational symmetry, we're going to take this vertex over here and rotate it to this vertex. And we'll get the same thing. Each vertex will rotate to the next one, and it's going to land on top of itself. So basically, each one of these central angles is going to be a rotational symmetry, which means this first one is, if we do 2 of them, that's going to be a rotational symmetry. If we do 3 of them, that's also going to be a rotational symmetry. All the way until we get back around. So 72 degrees will be our first one. And then we go 144. So from here to here is going to be 72 plus 72. And then we add 72 again and we get 216. We add 72 again and we get 288. And then we add 72 again and we get 360. Now, do you remember why we don't include 360? We said that 360 was a trivial angle of rotation because everything rotates onto itself at 360 degrees. So we don't list 360 generally. These are only the non-trivial rotational angles. So what would the non-trivial rotational angles of symmetry be for a regular hexagon? Can you figure that out? So let's see, we have 360 divided by 60. Oops, not divided by 60, divided by 6. We said is 60. So we're just going to add 60 over and over. 60, 120, 180, 240, 300, 360. We say, oh, 360, we don't include that one. So then we stop. So those are all of our rotational angles of symmetry for a regular hexagon. So just to list those steps out again, what we just did, we took 360 divided by the number of sides. We called that a central angle. And then we list it. We multiply that by 2. We multiply that by 3. And we just keep going until we get to 360. And then we cross out 360 because that one's trivial. But do remember, once again, this only works for regular polygons. If we draw some weird polygon like this, that does not have rotational symmetry. This only works for regular polygons, same side lengths, same angle measures. So let's give a couple of these a try. List all the rotational angles of symmetry for a regular octagon. Pause the video, list out all the rotational symmetry angles, and then come back and see if we get the same answer. So we're going to take the full 360 of a circle, divide it by 8. We get 45. We put that in our calculator. And then we add 45 a bunch of times. So we have 45, 90, 135, 180, 225, 270, 315, I believe, and 360. Oh, there's our 360. We don't include that one. So that is all the angles of rotational symmetry for a regular octagon. We didn't even have to draw those lines. We could draw them if it helps us visualize it. That's totally fine. But we didn't have to draw them. Let's try one more. This one's a little odd. We don't see this one very often. A regular nonagon. 9 equal sides, 9 equal angles. Pause the video, see if you can come up with the list. So we have 360 in the full circle divided by 9. That is 40. So now we just add 40 to itself a bunch of times. 40, 80, 120, 160, 200, 240, 280, 320, 360. Oh, we stop there. We don't include 360 because that one's trivial. So there is our full list of rotational angles of symmetry for a regular nonagon. Notice there are 9 of these as well. 1, 2, 3, 4, 5, 6, 7, 8, 9. That makes sense because we're basically just moving each vertex to the next one, right? This one to this one is 1, then 2, then 3, then 4, all the way around until it gets back to itself, so that we would count 9 of those vertices, because there are 9 vertices total. But one of them, the 360, the full rotation, doesn't count. So the number of rotational angles of symmetry will always be 1 fewer than the number of sides. Always be n minus 1 for any n-gon. Just something you can store in the back of your mind. You can always list them out like this. So that wraps up our objective for today. I can describe the symmetries of a regular polygon in 2 out of 2 problems.